So I'm trying to transmit this original image from this Windows laptop to that Ubuntu laptop, and both laptops have both my encoder and my transmitter and receiver. So I'm just going to run the encoder here, and I'm going to start listening in the meantime with the receiver. So you can see it's starting to listen, and it's looking for sync pulse. And then I come back here and choose the image. I'm going to transmit, and very soon it's computing the encoding, and it's going to play the audio version of the image, and you should see it pop up here in this figure.
What's happening now?
It's really slow. It's still encoding.
Oh, it's waiting for the transmission to begin?
Yeah.
I see. Okay.
So I don't know why it usually doesn't take this long. So then you can see this one is sending the image, and this one is line by line creating the image back.
So it's actually making sense out of that sound and creating this picture?
Yeah, so it's converting the brightness of each pixel in like green, red, and blue values to sound, and it's transmitting.
Ah.
And actually, while we talk, we introduce noise on the signal, which you can see in the output.
Oops, sorry.
Yeah, one annoying thing was that this display thingy works differently on Ubuntu and Windows, so I actually had to debug to make the line-by-line display work twice.
Oh. Okay.
Yeah, so it's basically like a TV, so it took an image from this computer and just transferred it to that just by the sound.
That's pretty cool.
So the purpose of this project was to basically simulate or to create a transmitter and receiver for SoScan TV. So SoScan TV is a way to transmit images from one module to another module, and the way it works is that it converts the RGB values of the pixels of the image to frequencies, and these frequencies are in an audible range from 1500 to 2300 hertz. And the reason that we picked this range is, although the encoding format, which is like the way that the RGB values are converted to frequencies, called the Martin M1 format, even though this takes a long time to send the image, it takes 114 seconds, it gives us a very narrow bandwidth of about 3 kilohertz. So the Martin M1 format starts with a VIS packet, which is a unique set of tones that just indicates when the image starts. And it has leader tone, break tone, and then a start bit, and then some code, which is 44 decimal, which indicates that it's Martin M1, and it's transmitted least significant bit first. And then a parity bit, which in this case is even, and then a stop bit. And so each of these components have different frequencies, and that's how the receiver knows that it's the VIS packet. So then images, so once you're done transmitting the VIS packet, you can start transmitting the image. It's transmitted line by line, and each line consists of 320 pixels. The line starts with a sync and a separator pulse, and then you just transmit the green values, then the blue values, and the red values in order for all the pixels in a line. And then each pixel is about 21 samples because the sampling frequency is 44,100 hertz. And so, and separator pulses between each scan prevent any collisions, and the sync pulses in the beginning of each line prevent one shifted line from shifting the entire image. And so first you use a linear mapping to convert RGB values to frequencies, and then you would think that you could just create sinusoids of these frequencies and just transmit the pulses. But these sinusoids, if you try to concatenate them, the phase of that output will be discontinuous. So you do a form of FM modulation very similar to AFSK, in which you just create a pulse with the carrier of the center frequency 1900 hertz, and then you add that a scaled integral of the frequency vector that you create with the frequencies that represent your image. So using this Martin M1 format, I was able to successfully encode an image and transmit it. So you can see this nice fractal image, and this is an SSTV app that I downloaded, which decoded the image that I transmitted. So. And then the input image can be of any size. So first you have to resize it to that 256 by 320 because there's 256 lines of 320 pixels each. And then I found that when downsampling, an anti-aliasing filter was good, and for upsampling, bicubic interpolation gave a pretty noiseless output. So now the receiver. So to start the receiver, I wanted to just take the output of my transmitter and take that perfect input and just decode it and produce a decoded image. So I started by trying to take the FFT. So I took that entire image matrix and extracted the chunks that correspond to pixels, the red, green, and blue values separately. And for each chunk, I took the FFT, I found the argmax, which is the index of the dominant frequency component, and I used that to index into a frequency vector based on the bandwidth and center frequency. I created that frequency vector, and that would give me the frequency that corresponds to that chunk. And then once you get the frequency, you just use a linear mapping to map it back to the RGB value. Then you can recreate the image. But this was pretty noisy, so I tried several things. I took 3 pixels at a time instead of 1 because each pixel is only 21 samples, and a sinusoid itself is about 30 samples for a full cycle. So I tried overlapping, and then I also windowed this chunk. I used Kaiser and Chebyshev windows. And I filtered it using Gaussian and median filters, and then I zero padded it. I tried various zero pads, 1024, 2048, 8192. Any power of 2 seemed pretty good. But, and I even learned about some wavelet denoising and Wiener filters, but unfortunately I didn't really have time. The math is quite involved to implement this in code. But even after all of this, the output was still pretty noisy. So I decided to just give up on FFT and try something much simpler. So I just took that input formula that we used to create the modulated signal, and I reverse engineered it to produce the encoded signal. And then I used a Gaussian filter to remove noise, and I got beautiful results. But of course, this is with perfect input. So this is my simple demodulation technique. This is the math that I used to just reverse engineer the computation. And to account for a small amount of noise, this has very low noise tolerance. I took 3 samples at a time overlapping, and then I used a tolerance of 10% to see if these samples were within the mean. And if not, I just discarded them as invalid frequencies and moved on to the next value. And this technique wasn't perfect. You can play around with the tolerance, get different better or worse results, but using a Gaussian filter with a standard deviation of 1 for the Gaussian kernel, you get that perfect output that I showed before. So, but now I wanted to see what exactly I would get if I recorded a signal from the speakers using the microphone. So I played a pure tone signal of 1200 hertz, and then I recorded it with the microphone, and I printed and graphed these values. And as you can see, the human eye can make out a nice sinusoid, but you can clearly see there's noise in the sinusoid, and my simple demodulation technique will not be able to find the frequency accurately for a noisy signal. And this is the magnitude of an 8K FFT, and you can see that it's symmetric and it's centered about halfway. So that was pretty good. Yeah. So now I was trying to make my receiver keep listening in the background, and then when it heard the image start, it would start recording at that point. So this means that I could theoretically transmit from one laptop or a radio or something, and then listen to what's being played with this guy and receive it. So that's the actual television part of it. So first, to detect, I wanted to detect the sync pulse at the beginning of the first line. And so I used match filtering. So match filtering, you create a template pulse of whatever you're looking for. So in this case, I actually had to use sync plus separator because the sync is 1200 hertz and the BIS packet contains 1200 hertz components, but it does not contain 1500 hertz, which is the separator frequency. So I combined sync and separator to look for the beginning of the first line, and then I flipped and conjugated that and then convolved it. And what this does is the output of the convolution is maximum when what you're looking for overlaps with your signal. And so you get the argmax, and that tells you exactly where your signal is. And so then you can know what the size of the image is. And I got a pretty reliable match filter, and also, but because you're constantly recording in the background and you're finding the argmax, but every chunk that you record may not have a sync, but the argmax will still give you some maximum. So you have to use some threshold to basically see whether it is a valid sync. So I found that by trial and error and plotting, I found that a threshold of 40 worked well, and so I was able to find the sync and separator, and then pass the output to the decoder. Now, once I passed the output to the decoder, I started getting all kinds of errors, like divide by zero and math domain error. And then I realized that this is because my demodulation technique, which uses cosine inverse and things like that, it couldn't accept the noisy input from the speakers, which first of all was at much lower volume. It would just take the values out of range for a cosine inverse. So I had to actually change back to the FFT technique and try to perfect that and remove noise, because that technique would actually be able to detect the frequency even with noise. So again, I went back to trying many filters, and this time when I tried a Butterworth filter, I waited for an hour, and it didn't compute anything. So it just wasn't viable. It took way too long to compute. So I played around with some Gaussian and median filters again, and then I played around with the beta of the Kaiser window that I tried earlier, and a larger beta corresponds to a narrower main lobe, and so I found that a beta of 14 worked pretty well for me. And yes, you can still see some quantization noise and rippling, probably from the edges of the window and the way that interacts with the chunks. And I also found one other improvement which really helped, and that was thresholding my frequency values to 1500 and 2300, because sometimes the noise would take it out of that range, and then it would wrap around because of my mapping function. It would just give me negative values. So I thresholded, I just said, okay, it has to be, I flatlined it at those points, and that really helped. And then I mapped my frequencies back to the RGB values. And this is what you can see. This is the kind of output that I'm receiving. This image was one that I used many times to test at various points in this project. It was really good. And as you can see, even for very simple images and for more complex images, I can get a pretty reliable output with some rippling. And given more time, I'd want to explore wavelet denoising, because I learned so much about Wiener filters.